In this video, you will be studying spring potential energy. Our essential question is, what does it mean to do work? By the end of this video, you should be able to differentiate between gravitational and spring potential energy, relate the spring constant to the stiffness of a spring, and calculate the potential energy stored in a stretched or compressed spring. Spring potential energy is the energy stored due to the elongation or compression of a spring. Notice the x that we plug into the equation. Potential energy is 1/2 kx squared. The x is the difference in the current length of the spring to the uncompressed spring, what its equilibrium position would be. So whether it's compressed or elongated, that difference is our x, and the spring constant is going to be the same regardless of whether the spring is stretched or compressed. The spring constant can be found using the formula F equals kx. So the force applied to the spring is equal to the spring constant times x, how far that spring has been compressed or stretched. If the spring is very stiff, that means it's going to take a big force to change the distance a little bit, so the spring constant will be larger. The units for the spring constant, which is K, would be newtons per meter. So what force has to be applied to stretch or compress it a certain distance? A spring with a spring constant of 120 newtons per meter is compressed to a distance of 2.3 centimeters. We want to calculate the potential energy stored in the spring. In order to do that, we're going to use the equation PE equals 1/2 kx squared However, we need to realize that my x needs to be in meters, and right now it is in centimeters. So potential energy is going to be 1/2. K is 120, but x, 2.3 centimeters, needs to be converted to meters. So to convert to meters, I'm going to move the decimal point to the left 2, so 0.023 meters. And that x needs to be squared. So this gives us an ending value of 0.032 joules of potential energy. Here we're told a hockey stick stores 4.2 joules of potential energy when it is bent 3.1 centimeters. It tells us we are going to treat it as a spring because that's the only one we have to calculate an elastic potential energy at this point. And it's asking us for what is its spring constant. So remember, there are two equations for springs. PE equals 1/2 kx squared and force is equal to kx. We're not given a force, we are given a potential energy, so we can plug in 4.2 joules for my potential energy equals 1/2. We are looking for K, so I'm going to plug that in as my variable, and X, again, does need to be put into meters, so 0.031 meters, and that is squared, and I end up with K is equal to 8,700 newtons per meter. So remember, we have two equations that we can use when we're dealing with springs. Force equals K times X, or potential energy equals 1/2 kx squared. Remember, the x in both cases is the change in distance, the change in the length of the spring because of the force from its equilibrium position.